Okay, so in linear elastic fracture mechanics, we started with the Williams solution, and the Williams solution told us that if you have a sharp crack, then the stresses ahead of the crack at a small distance r at an angle theta, stresses in this small pillbox, for example, are given by sigma ij to k1 or k2 by root 2 pi r and an angular function of theta, and the displacements at the same point are given as k1 we have given the forms of these functions for mode 1, mode 2, and for the different stress and displacement components. Now we have also discussed that this term actually is one term in an infinite series, and this one term is the most dominant term close to the crack tip. It is far more dominant than the second term, which we have also calculated in one of the exams. Now, why is this dominant? It's dominant because it has this 1 by square root r singularity, which means that if I am in mode 1, so let's say I'm in mode 1 and I'm on theta equal to 0, then this factor you can see is 1 for sigma 2,2. So sigma 2,2 along theta equal to 0, which is this line, the x1 axis, is going to vary as k1 by root 2 pi r only, and that looks somewhat like this. So your sigma 2,2 is going to vary like this with x1 in front of the crack tip. So we have been living with the fact that these stresses are extremely high, and they actually tend to infinity as r tends to 0, and they tend to infinity as 1 by square root r. Now this is exactly where the need for elastoplastic fracture mechanics comes in. No material can actually withstand infinite stresses. So somewhere close to the tip of the crack, I am going to have yielding occurring at the crack tip. So somewhere here the yielding will occur, and yielding will occur when the stress or a measure of stress reaches something equal to the yield stress of the material. So this infinite stress cannot be sustained. It has to be cut off at some point of time, which means that in front of the crack tip you must have a zone which is no longer elastic but is plastic. No matter what kind of a material, the elastic solution itself tells you that there must be a plastic zone ahead of the crack tip. Now this leads us to a dilemma. Now the question is that if the solution is not entirely elastic and there is plasticity in it, then what have we done so far? What is LEFM all about? Where we have been assuming that everything is elastic everywhere, but now we are saying that it cannot be elastic very close to the crack tip, because that's where the material has to yield and cannot sustain, because it cannot sustain infinite stresses. So elastoplasticity, the need for elastoplasticity is actually underlined by the elastic solutions themselves, and we have to ask this question that what is the validity of linear elastic fracture mechanics if we accept the fact that at the tip of the crack you must have a plastic zone. So we accept the fact that it's not an elastic problem, it's actually elastoplastic problem. Then what is the meaning, what is the necessity of linear elastic fracture mechanics? Okay, so we will look at this question. So in this week what I'm going to do is I'm going to give you a flavor of what happens when there is yielding at the crack tip, and we will try to establish the importance of LEFM in spite of the fact that there is a plastic zone at the crack tip. That doesn't happen all the time, but in many important cases, the linear elastic fracture mechanics still remains valid, though there is always a plastic zone at the crack tip. But first, we will start with simplified estimates of what is the extent of this plastic zone. How much, how large is this plastic zone ahead of the crack tip? Okay, so the first, the most interesting estimates were given by Irwin, which are actually extremely simple, but they capture both qualitatively and quantitatively. They capture almost all features of plasticity that occurs at tip of cracks. So let us look at the solution. So here is the same geometry that we looked at when we looked at Williams solution. So this is an infinite body. There's an isolated crack here. This is the crack tip, and we know at the crack tip sigma 22 has this form where sigma 22 goes to k1 by goes to infinity at k as k1 by root 2 pi x1, that is at theta equal to 0, and this goes to infinity as x1 goes to 0. So that's what you see here. Now this solution is governed by a single parameter. This is the LEFM solution. This solution is governed by a single parameter, which is the stress intensity factor, and the stress intensity factor is the amplitude of the most dominant term in an infinite series, which is for theta equal to 0 this. So this is a single parameter, and the single parameter is related to the remote stress that we have applied, and as you increase the remote stress, the loading on the crack tip, or in other words the stress intensity factor K1 in this mode 1 problem, is going to increase. We also look at first a mode 1 problem, which is symmetric, which means that sigma 22 is the only remote stress that I have applied. Everything else at the remote boundaries, every other component of stress is equal to 0. So with this situation, now we have come to accept the fact that this is not allowable in a real material, and then the stress must be cut off somewhere. There must be a cutoff for the stress, and let us see what that implies for our crack tip. So Irwin gave this idea that you have a situation called, suppose I have a situation called small scale yielding, which we will call SSY. Suppose this situation is valid. What does it mean? It means that, well, you have a K dominant zone. K dominant zone is the zone in which the 1 by square root R field for stresses, the fact that sigma ij varies as 1 by square root R, where R is the radius of this K dominant zone, this assumption is valid. So K dominant zone is the zone where a single parameter representation of the crack tip elastic stress field is possible. It is also equivalently the zone where the most dominant term of the infinite series that constitutes the Williams solution is 1 by square root R, and it is significantly larger than the next most important term. So K dominant zone is the size of the K dominant zone is the size of the circle, of the radius of the circle, black circle, in which all these conditions are valid. Now we have plasticity at the crack tip. We must have plasticity at the crack tip because infinite stresses are not possible. But we assume that the plastic region at the crack tip is smaller than the K dominant zone. So you have a region in front of the crack tip where plasticity is going to occur, where elasticity is going to break down, but this red region where plasticity is going to occur is engulfed within this region of K dominance, and we call this situation as small scale yielding. That means K is determined by the remote stresses that you have applied, the remote stresses that you have applied on the body. That is what determines your K. And this region, the plastic region, is completely engulfed by K, which means that whatever happens inside the plastic region, the stresses and strains inside the plastic region are determined by K and K alone. So plasticity is controlled also by K, provided the inelastic zone or the zone of plasticity is much smaller than the zone of K dominance. And in what we are going to discuss in the next few slides, at least in this week, we'll assume that this situation, the small scale yielding situation, is valid for our material. The zone of K dominance is much larger than the zone of inelasticity that must occur at the tip of a crack. We will proceed with the understanding that in whatever we are going to say now, from now on, the small scale yielding assumption is always valid. Okay, now let us now try to see what are the stresses along the x1 axis. To do that, we will cut the body. Imagine that we cut the body and we throw away this lower part and draw the free body diagram of the upper part. So that's what I'm going to do. Okay, when you draw the free body diagram of the upper part, you must realize that the normal to this is 0, -1. So when this is traction free, sigma 22 and sigma 12 are both 0 when it's traction free. But only this part is traction free. Only this part is traction free where there is a crack. In front of the crack tip, you don't have a traction free situation because this crack is subjected. This crack tip is subjected to very high stresses according to linear elastic fracture mechanics. How high are the stresses? We know that sigma 22 along x1 varies as k1 by root 2 pi x1. This is how sigma 22 varies. And sigma 12 is equal to 0 on theta on x1 or theta equal to 0. So this is the situation. Therefore, T1, which is sigma 11 n1 plus sigma 12 n2, is equal to minus sigma 12, because n1 is equal to 0 and n2 is equal to -1 on the surface, and T2 is sigma 12 n1 plus sigma 22 n2. This is 0 and this is again equal to -1, so this is equal to minus sigma 22. So the traction on this surface has a component T2 which is in the minus x2 direction, and sigma 12 is equal to 0 on this face, so this is equal to 0. There is no T1 component in a mode 1 situation. So if I now draw the free body diagram of the upper part, this is how it's going to look, and this is the traction which varies as root 2 pi x1 in the x1 direction. So this is your traction T2, and T1 is equal to 0. So this is in the negative direction. So this is the magnitude of the traction. So it is important for you to understand why the traction variation on this is going to be like this. This is the integrated traction will give you the net force that is acting on this surface, and that net force must be equal and opposite to the net force that you have applied here. So under sigma 2 to infinity, which you have applied in the remote boundary, and this traction, the upper part of this mode 1 problem must be under equilibrium. So this is my free body diagram. This is the free body diagram assuming that only the single term, the first term of the Williams solution is enough for describing the stress state at the crack tip. Okay, now let us take this traction distribution. Let us take this traction distribution and plot it along x1. So we'll flip it and plot it along x1, and this is the dotted line is what it is. So now we have already made the point that along this somewhere you must have yield. Somewhere yielding must occur, and let that somewhere be here. So this is the maximum stress sigma 2 that the material can sustain. Let us call that sigma y. So at sigma y, the stress cannot go beyond sigma y for this particular material. Okay, so the stress will be cut off at sigma y, and then here under this region, this flat region, the maximum stress has been attained. So under the flat region, the maximum stress attained will be sigma y constant, and then again the shifted form of this curve will start to take effect, and we will have this 1 by square root r variation again at the end of the plastic zone. So this is a measure, this length is a measure of the size of the plastic zone that we are going to have in front of a crack tip when it is subjected to a load equivalent to a stress intensity factor of K1. Now, why does the 1 by square root r solution take off again? Take off at this point? That is because we have assumed that the size of this plastic zone, which is A plus B, is much smaller than the size of the zone of K dominance, and therefore after the plastic stress distribution is complete, the 1 by square root r or the K stress distribution must take over again. Okay, so the total plastic zone size, a measure of the plastic zone size, it's a simple measure, not an accurate one, is A by B. And what we are going to show, or what Irwin showed through the simple analysis, is A is actually equal to B, and this is equal to twice the plastic zone size, twice the size of the plastic zone. So actually, sorry, this is not right. So this is 2rp is equal to the A plus B, which is the approximate size of the plastic zone. So now we will try to estimate A and B. The way we will do it is to say that, look, I have not changed the load at the remote boundary, so the force that I have applied on the body remains the same. Therefore, the force that is needed to balance this should also remain the same. What was balancing it in the beginning? In the beginning, when I had assumed that linear elasticity is valid, this stress, this traction, integrated from 0 to infinity, was balancing the forces due to these remote tractions, sigma 2 to infinity. So that was what was balancing it. Now what is balancing it is the area under this curve, this truncated curve, which is constant up to A plus B, and then varies according to 1 by square root r as x1 increases. So the area under this curve, and the area under this curve must be the same because both of them balance the forces due to this remote loads. Let us first derive an estimate of Rp using the Tresca yield criteria. So you must have studied the Tresca yield criteria and the von Mises yield criteria. I'll assume that you have. So if you don't remember, please brush it up. The Tresca yield criteria says that plasticity happens when the maximum shear stress at a point in a body reaches a predetermined value equal to the shear yield stress, which is equivalent to stating that the maximum principal stress minus the minimum principal stress is equal to the yield stress sigma y in tension. So sigma y is the yield stress in tension, and sigma max minus sigma min must be equal to sigma y. In fact, sigma max minus sigma min by 2 is the maximum shear stress, and that has to be equal to the shear yield stress, which in case of Tresca is half of the yield stress in tension. But we will use the yield stress in tension, but because that's easier to measure. So we will write the Tresca yield criteria as sigma max minus sigma min equal to sigma y. So we have to look at what is sigma max and what is sigma min. Now in mode 1, which we are looking at, the stresses along this, so if I take a small pillbox here at a distance x1 from the origin according to linear elastic fracture mechanics, for mode 1 sigma 12 is equal to 0, so this is subjected to equibiaxial state of stress where sigma 11 and sigma 22 both are k1 by root 2 pi x1. So sigma 11 and sigma 22 are k by root 2 pi x1. There is no sigma 12, so these two are the principal stresses. So this and this sigma 1 and sigma 2 both are same, equal to k by root 2 pi x1. Now, so sigma max is either sigma 1 or sigma 2, and it is equal to k by root 2 pi x1. Now, if you have plane stress, then sigma 33, or the third principal that stress, is equal to 0 for plane stress. For plane stress, it is equal to 0, which means that sigma min in plane stress is equal to sigma 3. Sigma max is either sigma 1 or 2, and the difference between them has to be equal to sigma y. So this is equal to 0. Therefore, sigma 2 equal to sigma y is the point at which a Tresca material is going to yield in plane stress. I'm sorry, this is plane stress. So in plane stress, yield is going to happen at this point. What about plane strain? In plane strain, sigma min is again sigma 3, which is nu times sigma 1 plus sigma 2. Okay, so we have sigma 2 minus 2 nu sigma 2 is equal to sigma y, sigma max minus sigma min, that is 1 minus 2 nu sigma 2 equal to sigma y, which means yield will occur according to Tresca in plane strain when sigma y by 1 minus 2 nu is sigma 2 is equal to sigma y minus 1 minus 2 nu. So what we are going to do, what we are going to see is yield will occur when this sigma 22, which is also equal to sigma 2, attains either a value of sigma y in plane stress or sigma y by 1 minus 2 nu in case of plane strain. So that's where you will have to cut it off. So once it reaches sigma y in plane stress or sigma y by 1 minus 2 nu in plane strain, that's at this point, you have to have the maximum cap on the stress, and that cannot exceed this value. Now, this is where it cuts the linear elastic solution. Now, obviously, because this area is the gives you the force that balances the remotely applied stress. This area cannot balance that out. Cannot balance that out because this area is obviously smaller than the cross-hatched area is smaller than the single-hatched area. So obviously this has to extend further into the material, and then your linear elastic solution will come into being again. So this linear elastic solution is basically a shifted form of this graph. So from here you have shifted it by an amount a. So if this is k by root 2 pi x1, this this uh, this plot is k1 by root 2 pi x1 minus a, because this is the same graph shifted by an amount a. So uh, so the total load carried by this area, now this cross-hatched area, has to be now equal to the load carried by the single-hatched area. And that is possible. We will find out A and B based on this principle. Okay. Now, at x equal to A, we must have alpha sigma y, where alpha equal to 1 for plane stress and 1 by 1 minus 2 nu for plane strain. That has to be equal to k1 by root 2 pi a. So A is the point here at which this truncated curve cuts the linear elastic solution. So this gives me that A is equal to 1 by 2 pi k1 by alpha sigma y whole square. So this is the term that governs now the size of the plastic zone. So we will see this term over and over again. This is k1 by sigma y whole square, and this, if you see, it has units of k1 has units of, let's say, MPa root meter. So this is MPa square meter divided by sigma y has the MPa square, units of MPa, and so this is MPa square. So this will, and this has units of meter only. So this is a quantity that has units of length, and this is the length scale that is going to govern the size of the plastic zone in front of the crack tip in small scale yielding. Remember, in small scale yielding is very important, because only in small scale yielding you will have the situation that this curve at the end of the plastic zone is just a shifted form of the linear elastic stress variation. So this will be possible only in the small scale yielding situation. So in small scale yielding, k1 by sigma y, or in other words, how large the applied stress intensity factor is in proportion to the yield stress of the material, this quantity squared, which has units of length, is going to give you an idea of how big the plastic zone size is going to be, whether small scale yielding assumptions are at all valid or not. Okay, so this is your A, and now we need to find B. In order to find B, we will use the concept of areas. So we will say that the area under this curve, let's erase this. So this area will be given by integration of 0 to infinity so this is the green area. This has to be equal to the blue area, let's say, which is this area, and that will be equal to firstly this rectangle, which is sigma y times a plus b, and then a plus b to infinity k1 so this is the equation for balance of total forces given by the area under the green the area under the LEFM curve and the elastoplastic curve, and this yields, if you solve it out, it's very easy to do. This yields A is equal to B. So this length, and this length are equal, and therefore RP is equal to 2 times A. And we call this total size of the plastic zone 2RP rather than as RP. RP is where the plastic solution cuts the elastic one, and 2RP is the total size of the plastic zone. Okay, so we will use this concept later. Two quick points. The first one is that we are only finding an estimate of the plastic zone. This is not an accurate calculation, but this is a very clever calculation, let's say. So from the clever calculation, we will find an estimate of the plastic zone. So we will basically know what is 2RP like, what does it vary with. We already know that it's going to vary with K1 by sigma y whole square, and then there would be a constant here which will depend on various things, whether it's plane stress, plane strain, Tresca, von Mises, and so on. But it's going to tell us that overall this length scale K1 by sigma y whole square is very important in elastoplastic fracture mechanics. So that is an information that we are going to get from a simple solution which only looks at stresses along x1, though the stresses are infinite everywhere around the crack tip, right? So this is the first point. The second point is that we are using a situation where the sigma y, this sigma y is independent of the plastic strain. So in other words, we are using what is known as a perfectly plastic material. We're assuming that the material of the material in which the crack is residing is a perfectly plastic material which has a constant yield stress which does not vary with plastic strain. In many materials, in many metals, sigma y would be a function of the plastic strain, and therefore it will change as the plastic strain changes. So those are called hardening materials, and we will look at them later, maybe next week. Okay, so a perfectly plastic material, we will define a perfectly plastic material properly when we deal formally with plasticity, but right now just take it from me that we are assuming a perfectly plastic material for which sigma y is fixed. If you just to clarify it a little bit more, if you look at the stress strain curve of the material for a perfectly plastic material, it has an elastic part, and then it has a perfectly flat stress strain curve, which is where the stress is equal to sigma y. Any stress state above sigma y is inaccessible to this material, and this is a perfectly plastic material. Obviously, it's not it's not a realistic material, but it comes very close to what we know as extremely ductile materials like aluminium and copper. Okay, so with these two caveats, we will go on and look at the solution a little bit more. So we have already learned that A is equal to B. So 2rp is going to be 1 by alpha square pi, and this length scale reappears. This length scale is always there. Must sort of make it your friend. And for a typical value of, remember, alpha is equal to 1 for plane stress and 1 minus 1 by 2 nu for plane strain. And for a typical value of nu, which we have taken as 0.3, 1 by 3 is a typical value of nu for many metals. 2rp comes out to be 0.16 by pi k1 sigma y square for plane strain, and 1 by pi k1 by sigma y square for plane stress. And you immediately see that the plastic zone size in plane strain is much smaller than the plastic zone size in plane stress. So in plane strain, the plastic zone is small ahead of the crack tip, is much smaller than in case of plane stress. This estimate comes from the simplified Irwin analysis based on the Tresca yield criteria. If you change the yield criteria, the numbers in front of this k1 by sigma y square will change, but the nature of this deduction will still remain the same. So this is always true. For plane strain, you have much smaller plastic zone size. At the same applied K1, you have a much smaller plastic zone size than in case of plane stress. So when the material fails, when the crack starts to grow, we will have K1 equal to K1C. At that point, your plastic zone size will be proportional to K1C by sigma y whole square. So this is a parameter that is going to tell you whether small scale yielding assumptions are valid. When this quantity is large, remember this is units of length. So this whole thing has units of length, and K1C is an experimentally determined parameter. Sigma y is also an experimentally determined parameter. So for any material, you can calculate this quantity. Once you calculate this quantity and see that it is probably very large compared to what you expect is the size of K dominant zone, then you know that small scale yielding does not occur. On the other hand, if it's very small, you know that small scale yielding is probably possible. So it all depends on the ratio between the fracture toughness of the material and the yield stress of the material. So this ratio determines whether you can assume a problem to be small scale yielding or it is not a small scale yielding problem, it's a large scale yielding problem. So that decision has to be determined by calculating this ratio. Now let us look at the stresses all around. So far in the Irwin solution, we have looked at only along x1. So these are curves that vary only along x1, and we have not looked at the theta variation. We have concentrated on theta equal to 0 and have got all our deductions with theta equal to 0. So now let us look at all the stresses. So these are all the stresses that you have, and you have sigma RR, which is K1 by square root R and then angular function, similar here, and this is your Mohr circle expression that will give you sigma 1, 2. So the plus will give you sigma 1, the minus will give you sigma 2. Sigma 3 is going to be 0 for plane stress, and sigma 3 is going to be nu times sigma RR plus sigma theta theta for plane strain, right? So So we can find sigma 1, 2 from here, and if I plug in the mode 1 dominant terms for sigma RR, sigma theta theta, and sigma R theta here, then you can easily show that these two are the principal stresses, sigma 1 and sigma 2. Sigma 3, as I said, has to be 0 for plane stress and is equal to nu times sigma 1 plus sigma 2 for plane strain. So these are the principal stresses in the plane, not at x1 but all around the crack tip. So it has a theta variation built in also. So now we can use this to calculate the shape of the plastic zone around the crack tip. Given that shape of the plastic zone around the crack tip, given the Tresca yield criteria. So the Tresca yield criteria is sigma max minus sigma min is equal to sigma y. This is the Tresca yield criteria. We are going to use this. So when we use this, what we see is for plane stress, sigma max is always equal to sigma 2. So sigma max is always equal to sigma 2, and sigma min is equal to 0, which is equal to sigma 3. Okay, so the maximum shear stress, maximum principal shear stress occurs in the 2-3 plane. In plane strain, let's assume some value of nu. In the upper half, here I have plotted the 3 stresses in plane strain, and in the upper half, sigma 1 is greater than sigma 3 is greater than sigma 2. So sigma 3 is the black curve, sigma 2 is the red curve, and sigma 1 is the blue curve. So in plane strain, sigma 1, sigma 3, sigma 2 is the ordering, and therefore sigma max is 1 and sigma min is 2. That means the principal shear stress, which is half sigma 1 minus sigma 2, occurs in the 1-2 plane. In the lower half, sigma 2 is the largest, sigma 3 is intermediate, and sigma 1 is minimum, and therefore sigma 2 minus sigma 1 gives you the maximum principal shear stress, which again occurs on 1-2 plane. So in plane strain in general, in perfect plane strain situations, the yield according to Tresca will occur in the plane of the maximum shear stress will occur in the plane, and therefore yield will occur in the plane of the crack, whereas in plane stress it is more likely to occur in the perpendicular plane, that is the 2-3 plane. The 2-3 plane is the plane perpendicular to the slide. So also we know that the plane strain plastic zone is much larger than, even from the Irwin simple Irwin estimate, we have seen that the plane strain plastic zone is much smaller than the plane stress plastic zone. So when you take a thick material, so this is the width of the material, let's say it's B, and then here's a crack. So this is the crack front, and it runs through the thickness B, and I have cut out the front part of the body so that we can see the plastic zone shapes. So at the center of the specimen, far away from the boundaries, remember at the boundaries this stress is equal to 0 because the normal is in the n3 direction and this is a traction free surface. So sigma 3 is almost equal to 0 at the surface, and therefore at the surface you have close to plane stress conditions prevailing. Whereas in the middle of the specimen, sigma 3 is not necessarily equal to 0. At the middle of the specimen, at this point, if you take the stress state, this point believes that it's sitting in almost an infinite material, and therefore this point is more like a plane strain situation, and therefore the plastic zone shape at the middle of at the center of this body is going to be much smaller because it's in plane strain than the plastic zone on the surface of the body, which is more in a plane stress kind of condition. So at the midst thickness you will have a small plastic zone, smaller plastic zone, and at the surfaces you will have a larger plastic zone. So if you have some way of seeing the plastic zones visually, you will see a much larger plastic zone when you look at the surface. Okay, so this is one deduction that you can immediately make. The other deduction that you can make is what we learned from here, that in plane stress, the maximum shear stress according to Tresca occurs in the 2-3 plane, whereas in plane strain it occurs in the 1-2 plane, and therefore the yielding which will occur along these planes of maximum shear in plane stress, which is for specimens of small thickness, plane stress will occur along the 2-3 plane in these directions, whereas in plane strain it will occur in 1-2 plane in these directions. So the yielded regions are likely to look like what I have drawn here, depending on whether this B is large or small. When B is large, you have a plane strain kind of situation. Things will happen. So yielding will happen in the manner shown on the right, whereas on plane stress, it is more likely to occur in the manner shown on the left. So obviously, things are not always exactly plane stress or plane strain, and in fact, fracture toughness from experiments which we will learn about a little later, fracture toughness of most materials will vary with the thickness of the test specimen. Though we have been saying that fracture toughness is a material property, what our discussion shows is that fracture toughness is going to be high for plane stress situations, where the specimen, where you use a thin specimen, B is small, than in a plane strain situation where B is large. So you will have a transition in the value of fracture toughnesses. This is for aluminium, by the way. So taken from this source. So you will have a transition region where you have neither plane strain, neither perfectly plane strain or perfectly plane stress, and there you will have a transition from a high fracture toughness value to a low fracture toughness value. So plane strain situations will underestimate the fracture toughness, plane stress situations will overestimate it, and you have to be aware of this fact. Okay, so this is all that you can get from the simple Tresca based Irwin estimate. We are going to make this more sophisticated so that finally we can look at even large scale yielding solutions. So we will do it in steps. In the next lecture, I'll look at what happens when you have von Mises.